So, final. To take home final, it's 5 questions, and most of the questions have 1 or 2 parts, or 2 or 3 parts, and all but one of them is a proof. I'll go through kind of an outline of what the questions are going to look like, and then I'll go back through and do one that's similar to each question. So that if you, basically, if you can do what I'm going to do here in class today, then you should be able to do what's on the final. There's one piece, and I'll point it out on question number 3, that I think is probably going to be the thinking piece. It's probably going to be the most challenging part of the final, but we'll get there. This is it. It's 6 pages long. It's not a big deal. It's basically 1 page, which is instructions, and then 1 page for each question. That makes it easy to score. I'll hand a copy to you that are here, and then I'll post it online, right? Probably before I even leave the building. I'll just post it so it's out there for you guys. Deadline on it is Thursday. So you have a whole week, 7 full days. And again, if you need another day or so, shoot me an email and say, gosh, I'm not done. I want to be done soon. Like, give me till the end of Saturday or whatever, and I can be flexible on that. I just need to get them scored and grades recorded before we go on the break, because I want you guys to not have to worry about it, and I also don't want to worry about it. So, hey, welcome. So, questions on logistics on the final? No, it's pretty straightforward. If it were me, what I would do is I would just do it on paper with a pencil, take a picture of it with my phone, and send it to me in an email. That's how I would do it, or scan it, or however you want to do it. If you want to open it up in Word and like type in your answers, that's fine too, whatever your preference is. But just so I can read it. There's one piece, and that's question number 5A, and it'll say that in here, where it's a GeoGebra file, and you could put an image in there and like I could just look at it, but I really want to manipulate it and like move the points around and make sure that it's all linked up together. And so I'm going to ask you to submit that in an email attachment as well. So 5A is going to be a separate submission that's just going to be that .ggb file that I can open up on GeoGebra on my computer, play with it for just a second, make sure everything's good, and then you should be good. So I should get an attachment with the test and then another attachment with the GeoGebra file. Again, for those of you that just came, if you prefer to just hand it to me, just stick it on my desk in my building. I'm at that 130 North building, which is about a block north of the district office, where they have that big training room. It used to be Farmington City, but it's like a 1-story kind of a rock front building, and you can just hand it to anybody in the building there and they'll get it to me. Trying to think, is there anything else, like, before we jump into content? Okay, let's jump into content then. We have about an hour and 20 minutes, and I want to get through at least 4 of these, because the 5th one is a lot like one that we did in the class. So, just to overview quickly what we have on the exam, what you're seeing on the screen right now is a summary of the 5 questions. So there's, and if you can't see this on the video, it's just in the notebook on the main page. Excuse me. So the question number 1 is going to be a pretty straightforward direct proof using circles and tangents and some of the rules for tangents and congruent triangles and angle, side, side, that kind of stuff, and corresponding parts of congruent triangles, CP, CTC. So it's going to look a lot like a lot of the proofs that we've already done in class. I'll do one like it today so that you can see it again, kind of refresh your memory on it, and it won't be the exact problem that we're doing, but it'll be pretty similar to the tune of, basically, if you can do this and think your way through an alternate approach to that same type of thinking, then you should be okay on number 1. Then there's just a second part on it, quadrilateral classification. Is it a trapezoid? Is it a pentagon? Not a pentagon, that's not a quadrilateral. Is it a parallelogram? Is it an isosceles trapezoid? Is it a kite? Is it a whatever? So that's kind of what we're going to be doing there. Question 2 is going to be our contrapositive proof where you assume it's false and then prove that that's impossible. And so if you're still struggling to wrap your head around that whole process, then question 2 is going to be tricky. I'm going to do one in class today that's a lot like question 2. The first part of it sets up a lot like question 2, and then as you get down the road a little bit into it, it's a little different. But it's a pretty straightforward, simple contrapositive proof. It's nothing super complicated. And this non-Euclidean geometry question is just a simple, give me a situation in the non-Euclidean world where you might have two lines that are perpendicular to the same line that go through the same point. We've talked about a couple of those in class. And I'll review that again when we go there. Question 3, I think, is going to be our thinker. That's going to be the one where you might be banging your head against the desk a little bit as you're working on it. I'm going to actually start question 3 during class today. I couldn't think of a question that was like question 3 that I could do because it's kind of a unique question, so I'm actually just going to start it. I'm going to get you going on the proof. You're going to get about halfway there. I'm going to give you some direction on where to go from there, and I'm going to let you finish the proof. It has 3 parts, but it's all kind of one concept. Question 4 is going to be our coordinate proof where we use slope formula, distance formula, midpoint formula, and kind of manipulate those x sub a's and y sub b's and all that kind of stuff, and use those formulas to determine whether lines are parallel, whether they're perpendicular, and that kind of stuff. Question 5 is our GeoGebra construction. It's really, really similar to one we did on November 17th, right up here on the screen. All those are in the notes, so I'm probably not going to spend too much time on that one today. I'll just refer you back to the class notes on that one. And that's it. There's 5 questions. I would guess that if you have a pretty solid mastery of the content that I've covered since I started on November 1st or whenever it was that I started, I can't remember, that the final will probably take maybe a couple hours by the time you write up all the proofs and check them and do all that kind of stuff. If you're struggling with some of the content, you might plan on a little bit more time because you might have to spend some time going back through notes or spending some time on YouTube looking up different proofs and the way that people prove things. And again, I'm totally okay with that. Use the online resources that are out there. I believe that these are unique enough questions that, like question 3, there's a bunch of stuff on question 3 out there. So if you get stuck on it, go look it up and see what you can do. Okay, that's the content overview. Ready to dive in question by question? Okay, question 1. Question 1 is going to be one that's really similar to one that we did on November 3rd. I'm actually going to bounce back in the notes to that one and kind of get started. So it was proof 3 where we have that tangents are congruent. So the question says this. I'm going to open this up on the screen and make it nice and big so we can see.
You said November 17th?
3rd. Well, November 17th is like question 5,
okay.
And November 3rd is like question 1. So question 1 is going to be pretty similar to this, where I have a circle and I have a couple of tangents on that circle, and the tangents intersect at some point off the circle, right over here at point C. And question 1 on the final is going to ask me to prove that this segment OC is an angle bisector of this angle, and that it's an angle bisector of this angle. So basically this segment is cutting this in half, and this segment is cutting this in half, which is visually intuitive, and that's the proof that you're going to be asked to do in question number 1. So as I review this thing that we did on November 3rd, you should be able to wrap your head around, okay, I'm going to start with that, and then I'm going to get to that angle thing. I'm not going to take you all the way there, because I need to see your thinking. But the bottom line is, and I'm going to actually go slow enough and write up I'm going to write out the actual proof the way that I would hope to see it written out. Again, not word for word, but give me just a second to... All right, I'm gonna actually just leave the markings up there. Maybe not. Okay, that's what I'm gonna do. So it's gonna say something like segment BC is tangent to circle O at point B, and segment AC is tangent to circle O at point B. Point A. So these two things are tangent. That's given. They're tangent. We're told it's tangent, so we get to use all the information that we know about tangents in order to help us prove this thing. Now, what this particular problem that we did on November 3rd is asking me to prove, it's asking me to prove that this segment is congruent to this segment. Okay, so prove that segment BC is congruent to segment AC. So, strategy on this one. Key strategy in a lot of geometric proofs is find congruent triangles. Once you find congruent triangles, you get congruent parts. Once you have congruent parts, you're done. In this case, right? If I can prove that orange is congruent to blue, then I can easily conclude that this segment's congruent to that segment because those are CPCTCs.
What do we want to use?
So I got to get congruent triangles. So I got side, I got angle, side, angle, and if it's a right triangle, I've got hypotenuse, leg, right? Which is going to be my baby for this one. Okay? How do I know it's a right triangle? That's my first conclusion that I need to justify. Where's my right angle? B and A, right? And I know that's true because tangents are perpendicular to the radius. Right? That's a theorem. We proved it. We know that tangents are perpendicular. So my first conclusion, you can see my line of thinking. I'm looking for congruent triangles, so I'm going to point out that certain parts of these things are congruent so that I can get a theorem here. So I know that angle B is, I know that angle B and angle A angle B and angle A are right angles because, and I would say that this because statement is a really important component for what I want to see when you're writing the final. If you just say angle B and angle A are right angles, you'll get partial credit. If you say angle B and angle A are right angles because, and you can say it however you want, I would say it like this. Tangents are perpendicular to radii. So my first conclusion tells me that this guy and that guy, are congruent.
And aren't AO and BO congruent because the radius is on the circle?
Yes. Right? So let's process the angle thing for just a second. Okay, we know the angles are there. Now with a right triangle, I just need the hypotenuse and one of the legs. Okay? Once I have the hypotenuses congruent and one of the legs congruent, then I've got congruent triangles. Well, the hypotenuses are easy on this one because it's the same segment for both triangles, right? So segment OC is congruent to itself. And that's my hypotenuse. Okay, so I'm going to go ahead and say that. Now, this isn't an absolute necessity for the written proof, but just to be completely explicit on everything, I'm going to say it. Segment OC is congruent to itself by the reflexive property. Okay? So that's my second conclusion. And, let's see, green didn't work very well on this board over here last time. So I'm going to use purple. I already started with green. And my third conclusion is, let's see, where's red? So I know that this segment is congruent to itself. And my third conclusion, I've got the hypotenuse, I've got the right angle, I need a leg, and Susan already pointed out that one of the the legs are pretty easy to show they're congruent, right?
Yeah, the radii.
Yeah, the radii. These guys right here, BO right here, and AO They're both radii of the circle, so we know they're congruent because radii are constant. So, and segment OB is congruent to segment OA because, always say because or by or something, because radii are congruent. Or you can say that 100 different ways, but just point out to me that you know that they're the same length because they're part of the circle. Okay, now do I have enough information to conclude that these two triangles are congruent? I do. By the hypotenuse leg theorem, I've got a hypotenuse and I've got a pair of legs and I've got a right triangle. So I know that because of the HL congruence postulate, or theorem, however you say it, by HL congruence theorem for right triangles, triangle, and get your letters in the right order here. Somebody help me out with the letters in the right order.
AOC.
So start with the right angle and go to the center and out to the end. AOC. Now start with the right angle. Go into the center and out to the end. And that's my 1, 2, 3, 4th conclusion. Now remember, the thing that I was trying to prove is that BC, that top leg, is congruent to AC, that other leg on the bottom, right? And now that I have congruent triangles, I'm done. I just need to write it. BC is congruent to AC because of CPCTC, which is an abbreviation for the definition of congruence. So my final conclusion is that BC, segment BC, is congruent to segment AC and that's by virtue of corresponding parts of congruent triangles. So that is a 5-step direct circle-based proof that uses congruent triangles. Now, think in your head. Question number 1 on the exam starts very much like this, but instead of proving that those two things are congruent, that those two sides are congruent, I'm trying to prove angle bisection. It's pretty straightforward, actually. From this point, once I know these triangles are congruent, it's pretty easy to show that this angle and this angle are the same. Right? It's almost exactly the same proof. So question 1 is very similar to this one we did on November 3rd. It'll be the same number of, maybe one more step because you have to show congruent angles and then take it back to the definition.
You have to show the angle of
So you're gonna,
angles.
so I've asked you to tell me, I've asked you to prove that this bisects the big angle and it bisects the angle out here. So you have 2 angle bisection things. But once you have congruent triangles, it's just making 2 conclusions using the same reasoning.
Right.
Mm-hmm. And that right there, folks, is how we're going to do question number 1. Do you need a second before we go to 2? Sorry, I know it's weird to look at my face this close, but I have to check and make sure it's still going. What?
We just proved that these 2 triangles are congruent.
Yes.
And you say the question itself wants us to prove that angle BC and AOC are congruent.
Yes.
The fact that these 2 triangles are congruent just ain't the fact.
Yeah, I basically handed you question number 1's proof right here. Right, for the final, because but you just have to make the next conclusion, which is about those angles, right? So you've thought that through perfectly. Okay, that's question 1. Question 2 on the final.
That was your question?
Sorry. Did you have another question? Okay. Question number 2 has some weird stuff, because it's that contradiction proof. Okay, and I'm going to do one kind of like it.
Is it already in the notes, or?
It's in the notes. Yeah. Should have about everything in the notes at this point.
Remember what day it was?
No, this is actually, it's from today. It's in the notes for today.
Today.
Yeah. All right. Here's the proof. Prove that there is only one line through C, point C. I'm going to use an eraser here instead of my finger because we're going to find ourselves in a greasy little mess. Okay, given that picture, it'll explain a little more. It'll say, here's a segment and a point, and here's this. But given this situation right here, the conclusion is that there is only one line through this point, which is parallel to this one. This is basically one of Euclid's basic postulates that you guys talked about in your midterm exam. And we're going to prove this with contrapositive, which is that logical, tricky one, because we have to make up something in our head that doesn't exist and then prove that that's not possible. So on the test, you're going to do this. It's going to start with the exact same picture, but you're going to prove that there's one perpendicular line. Does that make sense? So I'm proving that there's one parallel line today. You're going to prove that there's one perpendicular line. The conclusion's a little different. The falsehood is a little bit different that you're going to be looking for, but you start the same way. So what we're going to do is we're going to consider two lines that go through point C that are both parallel to parallel to segment AB. So let L and K be lines through C that are parallel to segment AB. Okay, I've just got two lines. One of them goes right here, and one of them goes right there. Kind of. Here, watch this. Well, that's not working. Okay. Woo. Here's L. Here's K. Now what I'm saying is that this one's parallel to this one, and this one also parallel to that one. Right? Now it's not possible, but
shouldn't one of them actually be parallel though?
Doesn't matter. Because whatever I'm drawing up here is a lie anyway, right? You want this one to be parallel just because, huh? So I'll actually do that. But for the sake of the proof, it doesn't matter. So L is parallel to K, or L is parallel to AB, and K is parallel to AB. Now I'm going to just get some points for reference. Okay, so I'm going to say, all right, here's a point. Let point E be on. Sorry, don't write that down. Let point D be on line L, and point E be on line K. Let point F be on segment AB. Now remember, what I'm trying to do is prove an impossibility here. I have to prove that something's broken in my picture. So let's have point D, point E, and point F. Doesn't matter where those points are. Okay, now proof strategies. Think back to what we know about these lines. Okay, we know they're parallel, right? Parallel lines tell me what usually. How do I usually use the notion of parallel lines? If I were doing a coordinate proof, I'd be talking about equal slopes, right? Yeah. But I'm not doing a coordinate proof. So I'm probably talking about a transversal and like corresponding angles or alternate interior angles or something like that, right? Mm-hmm. Okay, so let's look at a transversal. Let's take this transversal right here, and we'll call that line CF. Good idea. So we know that segment CF, or line, we'll just call it line CF, is a transversal cutting through parallel lines. It's actually cutting through two sets of parallel lines. It's cutting through line L and AB, and it's cutting through line K and AB. Right? Because L and K are both parallel to AB in our little world. So now, using what we know about transversals cutting through parallel lines, which is that corresponding angles are congruent, alternate interior angles are congruent, same side interior angles are supplementary, all that stuff. So using that information, I'm going to find a falsehood here. And that falsehood is going to be the thing that concludes my proof. So just for a minute, pretend like line L doesn't exist, okay? And just look at line K and the purple line and line AB. Do you see this angle right here? Okay, what's the alternate interior angle to that one up here? I'm going to make C bigger so we can see it. Okay? Angle ECF is the alternate interior angle, right? So I know that angle ECF is congruent to angle CFA. That's my first big conclusion. Angle ECF is congruent to angle CFA because parallel lines because alternate interior angles are congruent when parallel lines are cut by a transversal. Alternate interior angles are congruent. On an angle, no, but I probably should just say AFC just to be sure that if I were doing triangles, then it would really matter because the order matters. But this time I will just for pattern's sake. So I've got those are congruent, okay? Now I also know that line L is parallel to line AB. So this angle right here, okay, that red angle that I've marked, is also an alternate interior angle with that one. So ignore line K for a minute, pretend like it doesn't exist, and pretend like that line was parallel. They'd be alternate interior angles, right?
Right.
So I assumed that they were parallel, so I know they're congruent. So I also know that angle DCF is congruent to angle AFC because alternate interior angles are congruent, and I'm totally fine if you want to do that on the final, just as long as you think I know what you're talking about. If you don't want to write it again. This isn't a handwriting contest. You could say similarly, angle DCF is congruent to angle AFC. All right. Okay, now articulating the falsehood is probably the trickiest part about these whole proofs right here, because I can see what the problem is, right? If this one, let's point over here if the red one's congruent to the red one, and the green one's congruent to the green one, and the red one is the green one, then the red one's congruent to the green one. But I have this ray in between the red angle, right? That's cutting right down the middle of my red angle, and it's forming an angle that's congruent, which doesn't work, right? So I have to articulate that somehow, and that's the hard part. So in this one, what do I use when I have two angles with one angle cutting up the middle of them? Say that one more time.
Bisector?
Close. It's not the bisector because it doesn't cut it exactly in half, but it's the angle addition postulate. It's like this one. Okay, look, I'm gonna use colors real quick. Green plus purple equals red. Right? So I know, let's write that down. This is the angle addition postulate. Angle addition Yep, you did. States that, now I'm going to be careful. I'm going to go measure of angle DCF equals the measure of angle DCE plus the measure of angle ECF. Everybody okay with that? Yeah, you bet.
like, it can't be added because it's supposed to be forward.
So my problem is that DCF and ECF are congruent. So I'm telling you that something is equal to something plus the original thing, right? It's like A equals X plus A. That means that X has to be 0, right? Well, on my picture, it's not 0. So now I have my contradiction. My contradiction is that the two angles are, so angle DCF is congruent to this angle, so this statement is an impossibility. Because I can't have a non-zero angle added to something else and get the same answer. So to articulate that, I would say, since angle DCF is congruent to angle ECF, okay, we have a contradiction. And that contradiction is this angle DCE that's right in here, this purple angle, which in reality doesn't exist. It only exists in this broken world, which I built on my assumptions that those two lines are both parallel. So now that I know that that angle doesn't exist, I know that this whole situation is false, which means that these two lines can't exist separately from each other. They are the same line. And I'm good. So all you do is you assume, once you assume that there are two lines, once you find a contradiction, you're done.
So on the test, it's the perpendicular, so we draw two perpendicular lines.
Yep.
And do pretty much the same thing.
Pretty much the same thing up until this point. Instead of having a transversal cutting through parallel lines, right, you're going to have two perpendiculars. I might even draw a picture for you of what it might look like. Okay. Is everybody okay if I erase this guy over here? All right. If you're watching this on the video, just pause it. Well, rewind it first. So, I guess I'm kind of starting the question for you, but here's how you do it. I'm going to get two lines that go through here, and they're both perpendicular. Whoops. Okay. Boom. This one's a lot easier, actually. My contradiction is it's right in front of your face. You just have to find it. You don't have to do transversals. You don't have to do alternate interior angles. You don't have to do any of that stuff on this particular example. The contradiction is right in front of your face once you draw that. You have to cite it. You have to articulate it, write it down, and you're done. Okay? And it has to do with the fact that this is a triangle that doesn't exist, right? Okay, that's all I'm saying on that one, because I think I basically just handed it to you. That's question number 2. Question number 3, how are we on time? 8:05, we're good. Still recording? Yes. Hopefully audio is still going. Actually, I think I can test it. Testing, still good. All right, that's number 2. Number 3. Number 3 is the one, you guys okay if I erase this one? Mm-hmm. Number 3 is the one where I would imagine is probably the trickiest one. Because it's slightly different than other stuff that we've done. The postulates and the theorems are all the same, but the layout of the question's a little different than what we've done in the past. Basically, it says this. In right triangle ABC, angle A is a right angle. And D is on BC, segment BC, such that segment AD is perpendicular to segment BC. I'll draw a picture of it. While I get this ready, I'm actually going to put up a picture of it. I'm just going to pop it up here on the screen. Visualize it in your head. I can't take it too far on this one because I don't want to tip my hand too much on the... Tip my hand or tip my hat, whatever it is.
We don't mind.
You don't mind, I know. I told you you would pass this class, and today is the reason why you're going to pass this class. Alan's going to be like, why did everybody get an A in the class? Well, because they are awesome, Alan. That's why. Okay, I'm just going to put I already made it in GeoGebra, so I'm going to just put it up here for us. I'll be better off if I don't try to draw this by hand. And again, I have these drawings on the final too, so you don't have to. The only one you have to draw on your own is the one that's the GeoGebra one. Okay, letters are kind of small, but here I have point A. That's a right angle. Here I have point C. Here I have point D. And that's a right angle. And here I have point B. Let's make sure and restate this one right here. So I have right triangle ABC. Angle A is the right angle. So look at the big out exterior triangle. That's a right triangle. It's just laying on its hypotenuse, right? Most of the time I see right triangles drawn up this way. This one's laying down on its hypotenuse. Point D is on the hypotenuse, segment BC. And it's in a special place so that AD is perpendicular to the hypotenuse. It's the altitude of the right triangle. In fact, this whole thing has to do with the altitude of a right triangle coming from the right angle. So the proof is 3 parts, right? And I'll probably take you almost all the way through the first part, and then I'll give you some clues on the second and third part. Prove that. Triangle BAC is similar. Remember, the congruent without the equal sign means similar. Mm-hmm. BAC is similar to triangle ADC. Now for me, the hardest part about this proof is visualizing exactly what they're asking me. So my strategy, if I can't visualize it, is to break those triangles apart and draw them separately and draw them so that they're oriented the right way so that it all looks right to me. Okay, so you see 2 triangles. There's actually 3 triangles, right? There's this little triangle, there's this little triangle, and then there's the great big triangle. And I'm trying to show that baby triangle is similar to daddy triangle. And I'll work with mommy triangle later. Okay? I know. I thought about that one all the way here. Like, I had 15-minute drive. I'm like, how am I going to... Okay, baby, daddy, mommy, of course. Right? Like the 3 bears. I'd like to say that was a literary reference, but I don't think it counts. So I'm going to show that this little blue guy right here is congruent to this big black triangle that makes up the entire shape. So I'm going to draw them separate. I'm going to do that right over here. Okay? So here's my black triangle. I'm going to orient my black triangle a little different. I'm going to put the right angle in the left-hand corner so that it's oriented just like my other one. I'm going to put my blue triangle. I'm not going to draw them to scale because it doesn't really matter. This blue triangle is easy. It's ADC because it looks just exact. I just moved it, slid it right over. Now my black triangle, I kind of have to tip it up and flip it over a little bit because I want the right angles to be visually in the same place. So what is the letter that goes up here?
B.
B, and this one?
A.
And that one?
C.
C. I'm going to write that down. I want you to think about it and make sure that you're with me.
C or D?
It's C, because if I were doing mommy triangle, then D would be the right angle.
Okay.
Right? But I'm doing daddy triangle, so A is the right angle. Daddy triangle is this great big triangle right here. That's not an official mathematics term, daddy triangle, just so you know. Should be. Okay, when I write a geometry book, I'm going to make it an official geometry term. Daddy triangle, mommy triangle, baby triangle. So daddy triangle is this great big black one. Baby triangle is a little blue one. And I have the triangles rewritten over there. Basically what I did, here, let me do this with markers. Ooh, let's see how good I am. This is hard because it's 3. Okay. 3, 1, and 2. I need more markers. She only gave me 5. That's okay. Okay. Pretend like this works, right? Let's do this. Okay, there's my right triangle. That's how it is right now. That's daddy triangle, right? Mm-hmm. Okay. I'm going to tip it up like this and then flip it over like that. See how I did that? So here it is with the right angle. I'm going to rotate it clockwise until the right angle's on the bottom, and then I have to flip it over this direction. I have to do a reflection of that. So do a rotation and a reflection in order to orient it so it looks just like this. I did that on purpose. Okay, so my big long line, my hypotenuse right here, okay, I want to make this black triangle look in the same, make it so it's oriented in the same position as the blue triangle. So I'm basically just going to rotate it and flip it. Okay, if you have to, when you're doing this, make one of these suckers out of paper, okay, cut it into a little piece, and then move it around on your table and flip it over until you get it to look the way you want it. All right, any concerns so far about what I've done? Okay, now my goal is to prove that those two triangles are similar. My similarity theorem says that I need 2 congruent angles. Remember AA similarity? Okay, one of the angles is a piece of cake, and the other angle is almost a piece of cake. The one angle is a piece of cake because it's already there, the right angle. Okay, we're already there. We have one angle congruent. Now the other angle is pretty darn easy too, because if you look at just the black triangle, try to visually ignore the blue stuff, right? Angle C, right here. Now look at just the blue triangle, angle C. It's the same angle, right? Yeah. So I know over here that angle C is congruent to angle C, and I have to state that. So because angle C is congruent to angle C, right? You know what? I'm going to actually write those out. Look at your black triangle. What's the 3-letter reference for angle C? ACB. ACB, right? So angle ACB is congruent to angle DCA, and he did that right, okay? Because I went from the right angle in the black triangle to angle C to the other one, and I'm going from the right angle to angle C to the other one, angle DCA. Or you could look at it over here and say BCA. Wait, sorry, I did it wrong. ACB, DCA. Once I look over here, it's kind of easy to see. So that is because they're reflexive. Now, if you want to do it like I did the other one, where you said because of the reflexive property, that's fine. If you just want to put in parentheses and say reflexive, also fine. Either way, I know that you know what you're talking about. And I have another conclusion here. Angle BAC is congruent to angle ADC because they're right angles. I have 2 congruent angles, 2 sets of corresponding congruent angles, which means that triangle BAC is similar to triangle ADC by the AA similarity theorem. That's basically part A for question number 3 on the final. split those triangles apart, you kind of visualize them a little bit, and there we are. We use two angles whenever we're trying to prove that two triangles are similar. You can also use one angle, side, similarity also works. But the sides aren't congruent, they're proportional.
We don't have,
I don't have any of that stuff on the final. The one on the final is an angle. So, okay, part B on the final is going to be dealing with mommy triangle. Okay, that other one that we haven't talked about in this problem yet. This red triangle right here. This is part B. And guess what? They're all similar. The black triangle is similar to the blue triangle is similar to the red triangle. Okay? So part B, you're going to be working with the red triangle and proving its similarity.
which one?
To the blue one, I think. But it doesn't really matter because they're all similar.
And then part C is the other two?
No, part C is different. But process part B for just a minute. So I'm going to take this information that I have over here, right? And once I have this information, don't I know that this one is congruent to this one? Right? And once I have that this one is congruent to this one, then I have angle, and I'm done with part B. Right? You just have to reference it, get the angle, get the citations right, and everything like that. So you're going to use your work from part A, make an additional conclusion from that work in part A, which leads you to your conclusion for part B. Your conclusion for part B is that red triangle is similar to blue triangle. Now if it were me, I'd draw those guys separate again, just so that I have the order not mixed up. Because right now, this red triangle is actually tipped on its side. If I tip that guy up, then it's going to be oriented the same way that the blue triangle is. I draw them separate again. Part C is going to be dealing with the sides of those triangles. Okay? And what it's going to say is this. You're going to use the proportionality of the sides. Remember, proportionality of the sides means that if this is A, B, C, and D, okay, I know that A over B equals C over D. Or I know that A over C equals B over D. That relationship between the corresponding pairs of sides. This divided by this is this divided by this. That's part C, okay? You're going to just use that information to explore the relationship over here. Oh, you don't want me to erase it? Sorry. I had A, I think it's this one that you have to use on the final.
Yeah.
A over C and B over D. All right. So what you're going to do, if this is the hypotenuse, or let's not call that. Let's call that H, which is the height of the triangle. Okay? Let's call this segment right here A. And let's call this segment right here B. Okay? The relationship between those sides is that. And you're going to prove that for part C on the final. And that's the thinker. That's the hard one. Okay? Basically this. This is equal to this times this square rooted. Okay? It's not intuitive, but use your proportional sides, set it up, do some algebra, right? Cross multiply, solve it, see if you can get the height by itself, and you'll be on your way. I think on the final, I refer to this as like AD is equal to the square root of BD times DC. That's the notation that I use on the final. Okay, but it's the same idea. So part A is right here. I did part A for you. Part B, you're going to use mommy triangle. Part C, you're going to use the relationship between mommy and baby and those side proportionalities to do some algebra and get to that point right there. Okay. Can I erase this? Number 3. And again, I have that written out in the notes. It may not be like word for word exactly what I just did on the board, because I can't remember exactly how I labeled things and stuff in my notes, but it's there. Okay, question 4. Question 4 is our algebraic proof, and I'm going to do one like question 4 right now. I actually love question 4 a lot. Like, it makes me really happy. But you know how I feel about algebraic proofs too, right? Like, I don't even think it's in the curriculum for this course. I think I'm just teaching stuff that's not even... The university people would be like, what? He taught what? You guys were supposed to spend more time doing translations, but translations are dumb. So... Okay, this is going to be really hard to see. So let me kind of illustrate what I have here. Quadrilateral ABCD is given with coordinates as shown. And I'm going to write them over here so you can see them. Point A is x sub A, y sub A. Okay. Point B is x sub A plus P. And y sub A plus Q. Okay, where P and Q are just numbers. They're just numbers, just constant numbers. With P and Q being constants. Constants means just some fixed number. We just don't know what it is P, right? It's like 7 or 4. We don't know. So basically what I've done here is I've gone... I'm going to have to rewrite this, but just for a second, just visualize. I've come over P and up Q to get to B, right? So look at this x coordinate. It's where I started plus P, because I came over P, right? And my y coordinate is where I started plus Q, because I moved up Q. Think about it for just a sec. That's a right triangle. Yep. Everybody okay with the coordinates for point B? Okay, let's get the coordinates for point D. Right? For point D, I'm coming back Q. It's actually just Q because it's the distance, right? And I'm going up P. So the coordinates for point D, eventually I'm going to erase these because I'm going to want, maybe I won't. The coordinates for point D are x sub A minus Q. Remember I came back Q. And y sub A plus P.
Why did they split like Q up and B and one across?
Is it the same distance?
Yeah, so Q, so basically I went over P and then over here I went up P. Okay?
Why are you going up P instead of over?
If I go over P, then I'm not going to have the kind of quadrilateral that this problem is setting up for me. I'm just making sure we understand. This is given to us. These coordinates are given to us. I just want to make sure you understand what all the letters mean. Okay? Now, what you'll see on the test is exactly this, with the coordinates right there. Like, you don't have to find the coordinates because this is given to you. Given the quadrilateral with these coordinates, you're going to do you're going to prove some stuff with it. But for right now, I'm just making sure you understand where these coordinates come from. Now, C is the hardest one, just to kind of visualize, because I went to B, and then what did I do from B? I went back Q, right? And then I went up P. So I was at XA plus P, and then I went back Q. So XA plus P minus Q. That's my X coordinate. So I'm here. Think just in terms of right and left, right? How far to the right am I? Well, I'm XA plus P. That's how far I am right here. And I'm going to go XA plus P, and I'm going to back up Q. So that's this. XA plus P minus Q. That's my X coordinate. That's the location, that's how far horizontal my x is for C. So figure out the y coordinate.
YA minus Q.
Well, I'm already at YA plus Q, right?
Okay.
And then where do I go from that vertically? Plus P more, right?
Yeah.
So it's YA plus Q plus P more. So YA plus Q plus P.
So the outline of your quadrilateral is your hypotenuse on all of your triangles, and that's how you found your coordinates.
Yes. Yes. But I don't care. The triangles aren't the important part. The important part's the quadrilateral. But the triangles just help me visualize. When I look at XA plus P minus Q, I don't really know what that is until I realize that I started here, and then I went over P, and then I went back Q, and that's where I am. And this one, I started here, and I went up P, and then I went up Q more, and that's where I am.
Well, it's fine. I don't see how you went over P one way and over Q the other way. Isn't that the
It's
same
the
line
same number.
on your point D?
Did I write it down wrong?
How can you go P one way and Q the other way?
Well, I did. There's nothing that says that I have to go P. Well, I kind of do have to go P right now, but sorry. Big problem. You say stuff like that all the time in math class, right? Yeah, you go P, dude.
Did you go Q so that all of your hypotenuse would be...
I went Q so this sucker would be a square. Okay?
Okay.
That's why.
Okay.
I want to prove that it's a square, but I'm more worried about it being a rectangle, because what I really want is this over here. Just given that blue stuff right there,
Okay.
I'm going to prove that A, B, C, D is a rectangle. And this is what you're going to do for problem 4, except for instead of a rectangle, it's going to be a parallelogram. Okay?
Okay.
So it's going to look really similar to this, but instead of the plus P minus P, Q, Q, it's going to say something that will make this a parallelogram instead of a square. Okay? So I have coordinates, and I'm talking about angles and lines, right? What's the definition of a rectangle? It's quadrilateral that has what?
Two parallel.
Two parallel sides. That's a parallelogram, right? The opposite sides are parallel. But that's not unique to a rectangle.
90-degree angle.
All the angles are 90-degree angles. That's what it means. So the definition of rectangle is I need to show that every single one of those angles is a right angle. Okay? So we're doing a coordinate proof. Coordinate proof means distance formula, slope formula, midpoint formula. When we're talking about perpendicular lines, are we going to use the distance formula, the slope formula, or the midpoint formula?
Slope, you want the same slope?
Yeah, if we want to prove parallel, then we want the slopes to be equal. That's what you're going to do on question number 4 in the final. If you want to prove perpendicular, which is what we're doing here, then I want to use slope. I'm going to show that the slopes are opposite reciprocals of each other.
Perpendiculars for
Perpendicular means the slopes are opposite reciprocal. Okay? So here's my strategy. I'm going to prove that. Now for right now, that's just so we understood the coordinates. That's the only reason I had these little triangles in here, just so you could understand what the letters P and Q meant. So now I'm really only concerned with the blue rectangle, which I am trying to prove is a rectangle because I don't know for sure that it is. All right. I want to prove that segment CB is perpendicular to segment AB. Okay? So basically I want to prove this. I'm going to put a question mark in there because I don't know that for sure yet. And I want to prove that segment DC is perpendicular to segment CB. And I want to prove that segment DC is perpendicular to segment DA. And segment DA is perpendicular to segment AB. Would you agree that if I can prove that every single one of these pairs of lines segments is congruent, that I would be conclusive that that's a rectangle? Yeah, because if it has 4 right angles, it's a rectangle. Okay. Now the reality of this is, I really only have to prove one of them because the proof for all the other 3 is the exact same. So I can just prove one of them and say by similar reasoning, all the others are perpendicular too. So, if I want to prove that lines are perpendicular, and I'm in coordinate world, then I'm going to be using the slope formula. Remember that the slope formula is the second y minus the first y divided by the second x minus the first x.
Does it really matter in the order?
Nope, it can be first minus second. But it does matter that whatever you do on the top, you also do it on the bottom, right? Okay, so let's just pick a pair of lines. I don't care which one. Do you want to do the first one? Okay, so let's do this one right here. So we're going to do CB, and we're going to do, I need a color that you guys can read, red. This one right here. So we're working on this angle right here. So purple segment is perpendicular to the red segment. Well, let's find the slope of the purple segment, and let's find the slope of the red segment. Okay? So this is just a reminder of the slope formula. Okay? You don't even have to write that down for your proof, because for the sake of this discussion. So let's say the slope of BC is. Now this is where it's going to get kind of tricky. Now the way I've written this right here, C is my second point and B is my first point for the sake of this one. C is my second point. What's the y coordinate for C?
YA plus Q plus P.
Good. I'm going to put it in parentheses. And I want to make sure that everybody's following me. That's the y coordinate for the second point. And I'm going to subtract the y coordinate for the first point. The y coordinate for the first point is point B. That's going to be YA plus Q. Okay. So I took this minus this, which is y2 minus y1. This is actually not as ugly as it looks, because it'll simplify really fast. It'll clean up super quick. But now I got to do the bottom. I got to do the x's too, right? So I want to take my second x minus my first x right here. So that's going to be x sub a plus p minus q minus x sub a plus p. Now this is going to simplify up real nice. Okay. Plus p. Yeah, sorry, did I not write it clear? I might have misspoke. All right. Now, what's the mistake that your 8th grade students always make? They forget to subtract both of them, right? They just subtract that one. They don't distribute the subtraction or the negative one or whatever. We're not going to make that mistake, and we're just going to skip a step and jump right to the very simplification step, okay? YA minus YA, gone, right? Q minus Q, gone. What's left? P. Bottom. XA minus XA, gone. P minus P, gone. What's left? Minus Q. Don't make the same mistake your kids make. So the slope of that purple line is P over negative Q. Now I knew that because my rise was P and my run was backward Q, right? So P over negative Q. So just check it in your head, make sure it makes sense. Now let's do the slope of my red line, which is A to B.
YA plus Q.
So let's get, what's my second point is B, so now let's do this one minus that one, right? So it's YA plus Q minus YA, and then XA plus P minus XA, and that one simplifies real nice, because YA minus YA leaves Q, and XA minus XA leaves P. Do I have opposite reciprocals? Yes. So now I say, since the slope of AB and the slope of BC are opposite reciprocals, segment AB is perpendicular to segment BC, which means that I've done that one. Right?
And then you can say similarly.
No, I can, right? Now, really, if I were seriously thinking about it, then I would need to make sure to do them all. But remember my little triangles that I drew, right? The rise is P over negative Q. The rise is Q. Oh, sleepy time. That's what it was. I just got to wake it up. Wake up. Okay. So the rise here is P, negative Q. The rise here is Q, positive P, opposite reciprocals. So let's just visually check and make sure that we're good to say similarly so we don't have to do all that algebra mess. Let's look at these two lines right here. Okay? Rise over run is Q over P. Right? Rise over run is P over backward Q. Q over P, P over negative Q. I'm good, right? Now let's look at this one, right? The rise over run is Q over P. That's this one. And this one is P over negative Q. Am I good?
Yeah.
Okay, so I've got one, I got two, this one's done. This one's done. This one's done. Let's just verify this one real quick. This rise is P over negative Q for this purple guy. And this blue guy is Q over P. Good. Right? So now that I visually checked that, I can just say, similarly, all other angles are right angles. And A, B, C, D is a rectangle. Boop, done.
So if we have to prove this parallelogram, we're going to prove the opposite sides of parallel using make sure that the slopes are the same.
Yep. Yep. Instead of looking for opposite reciprocal slopes, you're going to, instead of doing these ones and finding opposite reciprocal slopes, you're going to do these ones and find equal slopes. You do this, equal slopes, it's parallelogram. So you do it twice, done. You do it once, you visually check the other one, right? Once the other one visually checks out, you say similarly the other ones are parallel too, parallelogram, done. Yeah. Right? Now, I could take this one step further. On the final, you're not going to. That's not just a rectangle, that's actually a square. Right? So how do I prove it's a square? Distance formula. Distance formula says a squared plus b squared is c squared, right? So p squared plus q squared is, now you guys know that this part, pause, this part's not on the final, I'm just showing you because it's fun. Right. This is equal to the square root of p squared plus q squared, right?
Right.
This is this length right here, q squared and p squared, negative q, but when I square it, it becomes positive, right? So this is equal to the square root of p squared plus q squared. This is equal to the square root of p squared plus q squared. This is equal to the square root of p squared plus q squared, and it's a square. So it's a rectangle which also happens to be a square. Now, could I have just done the distance formula and proven just this for a square? Or would I also need the angles? Is there such thing as a quadrilateral that has all four sides the same that isn't a square? It's a rhombus, right? Take a square, flatten it. That's a rhombus. So in order to prove, if this proof said, prove that it's a square, I would have to do this part, and then I have to go in and use the distance formula with all my xa's and p's and q's and subtract and simplify and prove, and then similarly, and then I would have a square. For the one on the exam, I'm giving you one of these that looks like a parallelogram with the coordinates listed kind of similarly to this. They're different because it's plus plus qp instead of minus pq, whatever. But you're going to use slopes to prove that it's a parallelogram. You guys feeling good about the final? Because you're 4/5 of the way done. You're 4/5 of the way done. with the final if you can do those. The ones I'm most worried about are 3 part C, that corresponding sides one, and the contrapositive proof, because that logical conclusion, well, I kind of basically just showed it to you. But articulating it and writing it might be tough.
So if you can follow kind of what we were thinking, you'd be okay.
Yeah, you might lose a couple points on notation or something like that. Each one of these is worth 20 points, right? So it's possible that if I can tell that you know what you're talking about, but you didn't write it down right, or some of your statements weren't clear, you could get 15 out of 20 on that one and get a 95 on the test, right? So I'll give partial credit. A majority of the credit will be for your line of thinking and whether it's clear that you know what you're talking about, and some of the credit will be whether the proof is articulated well and in conventions and stuff like that.
And you're going to average it with the midterm?
I will average it with the midterm if averaging it with the midterm helps you. And if averaging with the midterm hurts you, then I'm just going to use your final score and count it. So basically, I'll drop your midterm if it helps. And I'll use your midterm if it helps. Okay? Some of you did really well on the midterm, and some of you would probably prefer to just drop it.
I'd rather keep it.
Okay. Well, it depends on how you do on this.
Angela cheated.
Okay, question 5. We still recording? Are we still audioing? Testing?
No,
I think we're still good.
Very good. She's stressed.
Okay, question 5. GeoGebra construction involving rotations. So remember in class we did the angle of rotation, and there were like several different ways of doing it. This one is going to be where you're going to construct a triangle, ABC, and you're going to construct 2 perpendicular lines, and you're going to reflect the triangle over one of the lines, then you're going to reflect the triangle over the other line. Now intuitively that's no problem, but geogebraically it might be a little tricksy because you have to create the points and the perpendicular lines and the circles and the radii to find the image points and all that kind of stuff. We have time. Should I just go back to November 17th and just show you the one we did back then and just know that it's pretty similar to the one you're going to be doing? Okay. We have 13 minutes to do it, right? First piece is angle of rotation. Just read that. The second part of the question is about angle of rotation. You should be fine. November 17th. And all the dates are in the for today's notes, right? On today's notes it says for question 5 it's like the one on November 17th. So if you can't remember the date that I said, then there it is. Alan seriously might come back and be like, what'd you do? Taught a bunch of coordinate geometry, Alan. Duh. Should have thought about that. Okay, November 17th.
My eyes are so tired.
You know what? I'm going to start over on GeoGebra because it's easier to just draw a triangle than it is to mess with all that.
I'm just going to watch it on this one.
Yeah, the notes are all there. It's not really, like, it's not a super detailed step-by-step note, but you get the job done.
It's just that I went to the hospital.
Okay, triangle A, B, C. Make sure it's not an equilateral triangle, okay? Because otherwise it's going to be weird. And I've got 2 lines, one that goes like this. Oh, that's a triangle. And one that goes like this. D, E, F, G. Okay, everybody okay with that? Now on the final, I give you specific instructions to make these lines perpendicular, so make sure you do them perpendicular. This one doesn't matter. What you're going to do is you're going to reflect. You're going to reflect over one line, then you're going to reflect over the other line. Now reflections are basically this. Let's reflect over G first and then over F. So G's our first one. I'm going to actually hide line F for a minute. And as you're working, you can do that. See these blue dots over here? Just click the blue dot, it'll disappear, but then you can turn it back on later. So I'm just going to turn it off so I can focus just on this stuff. And I'm going to zoom out a teeny. Oh, I always do that. Did it again. All right. To reflect, what you want to do is you want to drop the perpendicular to the reflection line, okay? Then you want to use the compass tool to replicate that segment on the other side, like that. What that does is that guarantees that this distance right here is the same as that distance right there because they're radii of the circle and the circles are congruent. So you do that with all 3 points.
Can you show?
I'll show you how to do it on GeoGebra. Is that what you want? Okay, but theoretically that's what we're doing. We're dropping a perpendicular, then we're measuring this distance and repeating that distance over on the other side of the perpendicular. Okay, this is what it looks like on GeoGebra. I'm going to sit and do it. So I use my perpendicular line tool right here. If it's on a different one, just click the drop down and go to perpendicular and go from this point to that line. And I usually make it a dotted line just so that I don't get confused about what's going on because it's starting to get ugly. Okay, now I need that point of intersection. The reason I need that point of intersection is because I have to use my compass tool to measure the distance between those 2 points. Okay, so then I'm going to come up here to my circle area and get a compass tool. And I'm going to measure the distance between B and H, right? And I'm going to replicate that distance with H as my center. This looks a little different than what I drew. And get my point right over here, okay? Now point I, I'm going to rename that. I'm going to call it B prime prime. I should just call it B prime.
So basically you're drawing a circle and then your perpendicular line where it's tangent on the other side is B prime prime?
Yep. So this one over here is the image of B across the line.
Right.
Okay? I'm going to do the same thing for A and C. Perpendicular line from A to here. Okay? Point of intersection. Now, if you drew your triangle like this, then you're going to have a problem. See how that's going to be confusing, right? So if it was me, I'd just come and move it, right? Or just hide these guys because I'm done with them. I just need my point of intersection right here between those 2 lines. Oops, right there. What am I doing? Point of intersection right there. Now I'm going to use my compass tool. I'm going to measure from A to that point of intersection and repeat it. And my image point is right over here. It's the perpendicular that's the same distance. Okay, now I'm going to do point C. Point C is going to go the other way, right? This is the part that you might forget to get this little point of intersection right there. Once you get the point of intersection, you use your compass tool. Okay, that's my circle. My point C image is right over here. I'm going to rename that C prime prime. This one was B prime prime. And this one over here is A prime prime. Now my triangle, I go to the triangle tool, polygon tool, and it's going to go from A prime prime to B prime prime, careful on this one, to C prime prime, and back to A prime prime. And that's where I'm at. Okay? Everybody okay with that? It's ugly. But what I can do now is I can go in and shut all these guys off. And I can shut all these guys, oh, not that one. I can shut all these guys off because I don't need them anymore. I don't need point H, I, or K anymore, right? And in reality, I don't even need that triangle anymore, or these. I'll turn them back on in a minute. And I don't need this line because I already did it. I actually need that line, and I'm going to reflect them over that line. Because I have to do it twice, right?
But you didn't construct perpendicular lines to do it over, did you?
No, I didn't, but on the final you will.
Does it say go over y-axis first and then back.
It doesn't matter which one you do first. Because you'll get the same response either way. So now you do it again. I'll just do this one fast. Perpendicular line, right? Point of intersection, circle tool. Oops. Point of intersection again, that's my image. This is actually my final. That's going to be B prime, which is my final image. Perpendicular line tool, just going quick because we're doing the same thing, right? Somehow I didn't select it. Perpendicular line tool, point of intersection, compass, point of intersection, and that is my C prime, which is my final version of point C. Perpendicular bisector, point of intersection, compass tool. This point right here is going to be my A prime, which is my final image of point A. I come into my triangle tool. I'll make this one green, or I'll make it blue actually. Let's go from A prime to B prime to C prime back to A prime, right? Clean it up. I don't care if you're labeled, and I just like to clean it up so that everything looks nice, but you don't have to. But when you give it to me, this is what I want it to look like. J, L, and M. Again, the labels I don't care so much about. But
You want to see all three triangles?
A, B, C. That's what I want to see. Okay? So this you're going to save. You're going to email it to me.
You want that in a video or just that?
Just that. Because what I'm going to do is this. I'm going to open it up, and I'm going to get the finger thing right here, and I'm going to grab point A and I'm going to move it around. And if it moves the other guys around, then you did it right. Right? And I might even move this point right over to here and see how that does. And if it moves around and they stay the same, that's how I'm going to test and make sure that it did it right. And I may need to turn a couple things on and check, like if you're not quite.
You want the GeoGebra file?
I want the actual GeoGebra file. I'll open it up in GeoGebra on my machine and play with it, and if it looks good, you'll get credit. Okay? Now if one point's wrong, or if like one of the points didn't link up right with the other line, then you'll get partial credit. Again, 20 points on this one. There's actually another question on this one about angle of rotation that you'll need to go back to the notes and make sure you understand angle of rotation, how that compares to the angle between the lines and stuff like that. That's problem 5. 20 points apiece, 5 problems, 2 to 3 hours. I feel like I've given you a pretty darn good start on it. And you guys can reach out to me. So 1 week from today at 11:59 p.m. I need an emailed submission from all of you, or a hard copy delivered to my office. Questions? Okay. If you want a hard copy, come pick up a hard copy. Right there. I'm going to oh, not the top one. That's my copy.
No, I want that one.
Well, it doesn't have anything on it. It's just wrong. I made a correction and then reprinted it. So.
Thank you, Greg.
You bet. I'll post this video so you can go back and watch. I think, how long was that? 5 hours and 41 minutes? I don't think that makes sense.
Dang, well, we